Hi everyone. This is a talk about optics, a family of functional programming techniques, including lenses, that I will argue are vital to what we do as functional programmers, because it expands the range of problems for which functional programming is good at solving. However, many of the most common approaches, including the most popular libraries, while extremely powerful and elegant, carry a certain learning curve and cognitive burden that means a lot of people find it very, very hard to approach. On the other hand, there are a bunch of approaches that really focus on usability, but end up just being very limited and very domain specific in what they do and don't solve the general problem in a satisfying way. So I'm going to talk about the Monocle lens library in Scala and a macro that I wrote on top called goggles that hopefully gives us the best of both worlds, both the power of a fully powered lens library like Monocle and the ease of use of some of these other approaches. So we can take optics to the masses. See what you think. So let's talk about optics, and to introduce the concept I'm going to use the arcade classic Bubble Bobble. Hooray! The little green dinosaur, that's the player, and he blows bubbles and tries to ensnare the monsters in the bubbles. Now, if we were to implement this in a mutable way, this is a really terrible, naive way of doing it, but maybe there's a position class and an entity class and everything's mutable and horrible. But if we want to get some value from somewhere deep in the game graph. So if we want to get the player's position, we can do game.player1.pos.x and we'll just get back to position, and that's fine. But we don't even have to dig down into the structure. If we've got a pointer to that player, we can just directly get that value, that's fine. If we want to modify it, we can do plus equals 10, and it will modify it in memory, and that's fine. That'll all just do what we expect. SICP, if you turn to chapter 3, says, assignment leads us into a thicket of difficult conceptual issues. Well, we know all about that. Nevertheless, it is powerful technique for maintaining modular design. What is going on here? Since when does mutable state give us any kind of modularity? Well, it turns out there's a kind of a trade-off, a bit of a one-sided trade-off maybe. So in addition to all these bad things about mutable state, which I won't repeat because we all know how terrible it is, it actually does some things. And if you need those things, well, that's okay, it does that. It tracks state over time, so if we need to track a series of changing states for one thing, well, it does that. It instantly propagates changes to all observers at once without requiring any additional orchestration or arrangement. If you don't want that, that's a disaster, but if you do, well, it does that. On the other hand, if we write an immutable version of the same thing, as good functional programmers as we should, maybe we come up with something like this. So there's a pos class, a sum type. So in Scala, this is how we write a sum type of entity, and the entity can either be a monster, a player, or a bubble. And then a game thing that has all the other stuff in it. And once again, if we want to access a value, it's much the same. We can dig down into the structure and get the value. But if we want to change it, well, we're in a different place now. Because we can't just change something in place. We have to know about the whole structure. We have to know where it lives inside the whole structure. We have to know how to create everything on the way back out. We have to recreate the pos that has the X position, and the player that has the pos, and the game that has the player. And really, this is not very modular. We have to know all that stuff. And so it turns out immutable state, immutability, which is so great for so many reasons, which again I don't need to repeat to you, in fact there's a kind of a trade-off because it introduces some awkwardness for some kinds of problems. We need to manually orchestrate the position of nested states, nested structures. We need to know path information. We need to know where something exists within the broader structure. And a lot of code is written to do that. So this is all terribly embarrassing because functional programming is supposed to be all about modularity. That's meant to be the slam dunk win. So this is very embarrassing. So I guess we can throw up our hands and decide that FP is terrible at a bunch of really ordinary problems. Or we can use optics. So I'll start with the idea of a lens. And a lens is just a pair of functions, a getter and a setter. But our setter is not mutating anything, no. The setter is producing a new version of the structure, given the new value you want to set. So in our example, from the player, there's a function that gets the position from the player, but the so-called setter, in fact, that's just copying the player with the new thing inside it. And this is good because, well, we can make other lenses too. So from the position, we can make another lens that gets the x coordinate out of the position and another one for y, and we can compose these, just like we compose functions. Composability is one of these big ideas in functional programming, and if we're getting composable ideas out of something, we know we're onto a good thing. So we can fuse these two lenses together into one big lens, and just like composed functions, we don't have to care about that middle step anymore. And that's a good thing. So now, using pseudocode, I suppose, we can imagine we have three lenses to get the player, the position, and the x. We fuse them together into one lens. We can get that result, and to set it's the same thing, because each of those lenses already has the knowledge inside it of how to locate and copy things. And so just fusing those lenses together means that it's just saying, go modify that thing, and we're done. So, well, that seems to solve the problem, so that's good. But in fact, it's better than that because we get all these other concepts in tow. There's this idea of a prism, which is the dual of a lens, and that selects not piece of data that we have inside another structure, but a case of a sum type. So, for instance, we might have a game entity, which might be, it's either a player or a monster or a bubble, and we can select the case where it's a player. And so the getter, if you like, does a match, and if it's a player, it'll return the player, else it will return the original entity structure. And the set operation says, here's the new player that we want instead, and it will package it up as that concept on the other side, an entity. There's also this idea of a traversal, which we might think of as a kind of a lens that can focus on many things at once. So that's cool. And then there's I won't go into too much detail here. There's a bunch of different concepts like this, and they all relate to each other. We'll just cover a few. And ISO is sort of an equivalence between two things, like player 1 and player 2, for instance. And the great thing about this is they're all mutually composable. We can just smush them all together and they just click together like Lego. So we can have a lens that from the game returns a list of monsters, and then a traversable that focuses on all the monsters in that list at once, and then a lens that gets the embubblement status out of the monster, and we can squish them all together into one big traversal. And we need not consider what went into making that traversal, just like any good composable concept. So that's great, that's really powerful. And so yeah, if we did that, all of a sudden now we're selecting all the embubblement statuses at once. These concepts all relate to each other. This is a class diagram essentially. An ISO is a lens and a prism, and lenses and prisms are traversals. And the cardinality is in the purple there, so traversals is 0 to n, and yeah. Now, so there's a few more concepts like this as well, but it's not that many. You can learn them. It's not that many compared to your Gang of 4 book, for instance. So what's the problem? Obviously, I'm going to start complaining about something. Optics libraries, people find them hard to learn. And to examine why that might be, let's look at control.lens, the Haskell one. So we might implement a model much in the same way. So this is a bunch of records, and we say make lenses, make lenses, make lenses, make lenses. That will automatically generate the getters and setters essentially to make lenses for all these structures. And we might do something like this. View is a function packaged in the library that runs the lens. Score is a lens that selects the score from the game, and G is the game. So that will return us 1,000. Monsters is another lens that returns a list of monsters, and we'll get back that list of monsters. But then we can compose an each traversal with monsters, and it will focus on each monster in that list. This looks like function composition because it is. The representation of optics in Haskell are just functions, and they compose just like functions, and we can use them in all the ways that we can just use functions. And that's great. Now, we can keep composing stuff onto that. So we're focusing on each monster, and then we're focusing on the position inside each monster, and we can get back a list of positions, and then we can focus on X, and we get back a list of X values. Great. Setting is just as easy. We just say set with that lens with number 11, and it will set it within that structure. And then over lets you run whatever updating function. And there's also DSLs, which some people love and some people hate. But again, what's astonishing here is, so dot squiggle, that's our operator, which means set, but in fact it's all pure functional. Monsterpos.x is just one big function, and it only gets run when we pass it G, the game at the end. So that's astonishing. We've almost got back to that same syntactic elegance that we had at the start. And then, yeah, this is the same thing for an update function. And again, what's the problem? People find lenses hard to learn. They do. They just do. And to examine why this might be, let's look at the definition of that function in Haskell for lens. Now, if you know a bit of Haskell, you can nut your way through this. So there's 4 type parameters, S, T, A, B. There's some sort of action, F, and we're turning an action on small things, on the values, into an action on the big things. So you can sort of get through that, I guess. But if you're just coming to it straight away, that's, you know, it's a concept. Traversals are the same, except with an applicative constraint instead of functor. And again, you can sort of nut your way through this, but you don't have to go far before you hit things that are a bit harder to get through. So the very next thing on the page with lenses is into indexed lens. So all right, well, there's an I type, and the result is indexed by that, where there's some sort of action P that's indexable. And what's that? Okay, well, so P's conjoined, and then that's and we hit the wall. Now, I don't want to suggest that that's bad to use these ideas here. Category theory is an enormously rich source of ideas for programming. Nor would I suggest that you shouldn't learn them. This is an enormously good way to enrich your knowledge too. But it is unacceptable as a barrier to entry for updating the bubblement status in a list of bubble monsters. Boring problems demand boring solutions. So we need a way to harness all this power, but bring back the barrier to entry so that the amount of stuff we need to know can scale with what we're doing. However, now there's a bunch of other approaches to this problem as well, because immutability is not just something you find in Haskell programs. Clojure is a language that is a functional dynamic language, and it has such a strong focus on immutability that if immutable state was hard to deal with, Clojure would be incredibly painful to use. Now, I don't know if you've talked to a Clojure programmer recently, but they all seem really, really happy. So they must be doing something right. So we can look at this. Here is an immutable list of records with name and age. Get in, for get in, you provide a list of keys. So 0, it'll take the 0th entry, and then name, and we get back Linda. Update in, we provide, again, a list of keys, 1 and age, and then a function plus and an argument 1, and it'll update one of the age of Tom to 21. And inside the larger structure. This uses as an idea, in Clojure, this is the idea of an associative structure. And so anything that uses that interface can plug in there. Now, the thing is that this is great for Clojure. It makes a lot of sense for how Clojure programmers do things, but also it's quite limited. It solves a part of what optics solve, a part of that problem, but we don't get prisms, we don't get traversals. It does some idiosyncratic things with nil, because that's what you do in Clojure. It throws exceptions in certain situations, so you don't get that robust, type-safe, general solution for this problem that you would in an optics library. Next, I'll look at JQ. JQ is a command line tool for processing JSON, and users of JQ almost certainly don't think of themselves as functional programmers. And yet, what they are doing is functional programming. And again, we have that same record structure. Dot, square bracket 0, dot name. You know exactly what that does. Even if you've never seen JQ before, you know exactly what that does. 0 is the index, then dot name, and you get back Linda. Dot, brackets, dot age plus equals 1. So the brackets with no index in there just select all of them at once, just like a traversal. And then plus equals 1, you know what that does. So it's updating all of them at once, and then there's a setter 1 down the bottom as well. So this is doing a lot of what optics do. And we didn't have to learn any category theory or type classes or anything to achieve it. But it's domain specific. It's just for JSON, JSON concepts in this one little library. XPath, same thing again. /people, /person, 1 name. You know exactly what that does. But it's domain specific. This is Groovy. With a spread operator, *dot, it lets you run a method on all of those things in the list at once. But it's just for lists. It doesn't take this idea and take it to its conclusion, and you don't get to use it in some broader context. Null-safe operators in a bunch of different languages, I mean, really, they're prisms. They're selecting the possibility of it either being null or not null, and you're just going down the not null path. So the lesson here is that we can solve a bunch of the boring problems that optics solve without a lot of knowledge, and with using forms that are very, very familiar to a very, very large number of programs. However, not capturing the core concepts, these elegant composable ideas of optics, means that we end up with something very, very limited and frustrating that can't solve the problem all up. So why can't we have the best of both worlds? Monocle is a lens library in Scala, and it's very much in the vein of control.lens. It doesn't go quite as far with category theory, but it has all of these concepts that you would expect. So it's got lenses, traversals, prisms, and a bunch of other ones. There's only 8 of them, and again, you can learn it, you can get there. And there's ways of generating lenses, similar to the template Haskell that we saw before. So here, for pos, we might say gen lens, and that's a macro, and that'll automatically generate the getter and setter stuff. Or if you're feeling super, super magical, you can use this experimental compiler plugin, and the annotation will do it for you. Now, if you wade through that boilerplate, then we get to here. Because of a compiler bug in Scala, we can't just have a single composition operator. It's got to be compose, traversal, compose, lens, and so just as a barrier to entry, you need to know all of these concepts: folds, getters, setters, traversals, optionals, prisms, ISOs. You need to know them all up front. Now that, again, that is an unacceptable barrier to entry for updating the bubblement status in a bubble bowl game. So I've written a macro that sits on top of Monocle that lets you use all of that power of Monocle, which is a very well-designed library, but with a JQ-like syntax that's compiler checked and doesn't require a lot of knowledge to get started, that I'd like to introduce to you. So it looks very much like this. If you haven't seen this kind of thing before, in Scala you can hijack string literals so that there's a prefix that goes to the left of the literal, and that means that you can use the contents of the string to create whatever you want to create, and you can interpolate whatever things you want to interpolate. Now, if you make that a macro, you can fail that at compile time if people don't put the right stuff in the string. So essentially, you can make your own primitives. So here, this is compile checked, and so dot monsters will automatically generate a lens that gets the case class field of monsters out. Square brackets 1, you know what that does. It's an index. And then for set, it's just the same with a setting operator, but that's just regular Scala, that part. And it does what you expect. So the design principles are you already know how to use it, but then once you learn it, it gets out of the way of experts too. I will demonstrate it now in a command prompt. This is totally going to work. And you can be the judge. So this is that same game struct, bubble game structure that we saw before. So we can say get, interpolate the game, dot monsters. That generates a Monocle getter, and it'll get the monsters. Well, that's pretty boring because just regular game.monsters does that. But if we do star, that's each, does an each traversal, star.pos, then now we get back a list of positions. Star.pos.x, well, we get back a list of x values. Now, you don't have to learn any category theory to do this, but it doesn't stop you from getting to the stuff that uses category theory when you need it. Now, one of the great things about writing this as a macro is that I know a lot more about what the programmer is trying to do than the Scala compiler does. And that means we can provide really good compile error messages. If we have garbage that doesn't parse at all, I made the font too big. Okay. It prints a usage message. So that just tells you all the things you can do, sort of dot this, dot that, interpolate, indexes, and so forth. And if we do that whole structure and then have some rubbish on the end, you get back a table explaining every step and the types at every step, and then the optics that apply there too. So if you don't know what getters or traversals are, well, that's fine, you can ignore that column, or you can sort of start to get an idea of, okay, well, this is what's being created at each step, and this is what happens when you compose each one with each other one. If we do set, it's the same thing. So set, now we're going to set the x values to something big, and we get back all the structure with the x values updated. If we want to run whatever function, we just use a squiggle operator. That's maybe the most controversial operator choice in it, but SBT does it, it must be good. I shouldn't say that. Oh, no. Okay. So, yeah, that adds a function in there. So it's applying a modifying function as well. And there's, I've put in a couple of overrides. So for integers, you can do plus equals, and it's sort of the same sort of thing. Cool. Now, there's only a few basic things in the syntax, and that's how it should be, because that's the part that's solving boring problems. So we want that to be boring. But then when it's time to use all the rest of Monocle, which I have absolutely no intention of re-implementing, we can just interpolate Monocle stuff. So if I say val monsters lens equals gen lens from game to monsters, cool, that's a Monocle lens now. If we go to get this monsters part that's automatically generating a lens from the case class, I can replace that. I can interpolate monsters L. I can interpolate that Monocle thing, and that will just work. So we can take whatever Monocle things and just plug them in. If I say, and we can also create, there's one more verb here, lens, which will put them together to create another Monocle optic. So we can say monster pos L star dot pos. That, yeah, right. How do you Scala? What have I done? Monster pos. I've completely overridden the last thing. That's terrible, I think. Monsters, right, I'm referring to myself. That's a terrible thing to do. There we go. So I'm taking that last lens I defined, then putting in each traversal there, and then getting the pos, the position. And now we can interpolate that. So this one, we can just replace that whole thing with monster pos, is that what I called it? And it's the same thing. So you can make whatever optics you want at whatever level of abstraction, and it all just plugs into this DSL. So what does the future hold? Cool. Thanks, Microsoft. Yeah, good. Optics are here to stay. They are just too good to die off and fade into the sunset. More and more programmers around the world are learning about the benefits of immutability. And that's not going to change. But as they learn about it, they're going to hit the frustrations of immutability as well, the restrictions it places on you. Optics are the best solution that has emerged to this problem. On top of that, they give you vast abstractive power. Now, the usability problems that people have in learning it, these can be overcome, as I think I've shown with this macro, and I hope you agree. Built-in support, built-in language support is something that can deliver a lot of value here, because knowing that they're doing an optic-like thing, a lens-like thing, is so valuable in formulating a user interface for the programmer and error messages for the programmer, and a general language compiler can't do that without special support. So future languages will have built-in support for optics. It is going to happen. I don't know when it's going to happen. I don't know what it's going to look like. I hope this goggles macro can help this process along. I hope this is part of that ongoing process. And if you've got a Scala library going, why not give it a go? Monocle and goggles. If you've been hanging on the edge and you find Monocle a little bit daunting, perhaps this can be the gateway drug you need. Watch this space. More will come from the air. Thank you for your time.